Yeah.
So he's still presenting.
Should I stop it?
So for a second, we'll start the introductions and then you can present again and start.
Okay, fine. Okay. Yeah.
Yes. Good evening, everyone. A very warm welcome to all our space enthusiasts joining us from India and around the world for the day 6 of the World Space Week 2025. I am Amoli, and I'm thrilled to be your host this evening on behalf of Propagation Institute of Advanced Studies. I would like to tell you some notes. That is, please keep your microphones muted throughout the talk and kindly drop your questions in the chat box. They'll be taken up during the question answer session at the end. Now, World Space Week is the world's largest annual celebration of space science and technology, observed globally from October 4th to the 10th. This year's theme, Living in Space, encourages us to explore the opportunities and challenges of humanity's journey beyond the Earth. Throughout the week, we have explored astronaut training, astrobiology, citizen science, and stellar phenomena. And tonight, we dive into a new dimension of accessibility and innovation in space science. That's democratizing the sky. Now, I would like to say something about the organizers. Propagation Institute for Advanced Studies is a global platform connecting students, researchers, and educators in pursuit of scientific discovery. In collaboration with the Citizen Science Group, SA Citizen Science Group, India's largest citizen science community, we bring science to everyone, breaking barriers and opening doors to exploration. I would like to introduce our guest for today. We are honored to welcome you, sir, Professor Syed Hasan, Professor, Department of Mathematics, MANUU, former HOD, Astronomy, Osmania University, expert in celestial mechanics, dynamical astronomy, and Clifford algebra. With over 25 years of teaching and academic experience, Professor Hasan has been an active contributor to Olympiads, science outreach, and astronomy education, inspiring countless learners to look up and explore. Our today's session, Democratizing the Sky, the virtual observatory story, will explore how technology and open data are reshaping the way we access, analyze, and participate in astronomy. From professional research to citizen science-led discoveries, virtual observatories are breaking down walls and turning the cosmos into a shared laboratory for all. I welcome you all, sir. I welcome you, sir, and kindly take over the mic.
Thank you, ma'am, for giving me this chance to be with all of you. And thank you for the introduction. I'm very happy to be speaking to all of you. So let me congratulate and wish everyone a grand World Space Week, which is slowly coming to an end. But let's hope we celebrate this always, even beyond the week. So can you give me permission to?
So it's already there. Permission is there.
Yeah, just a minute. I'm unable to share the screen.
Again, okay.
Just a minute. Okay, yeah. I think I should be able to.
Yes, sir.
Yes, sir.
Yeah, okay. Yeah, so thank you for giving me this opportunity. And we'll be talking about the virtual observatories, democratizing the sky. So let's begin with this is not really an anecdote. See, this is a story which most people must have heard, that an astronomer, a physicist, and a mathematician are traveling in a train in Scotland. The astronomer looks out of the window, sees a black sheep standing in the field, and remarks, How odd? Scottish sheep are black. No, 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 says the physicist. Only some Scottish sheep are black. The mathematician rolls his eyes at his companions, muddled, thinking, and says, in Scotland, there is at least one field containing at least one sheep, at least one side of which appears black from here. Right? So this is not quite a joke. It's really a statement on saying how physicists, astronomers, and mathematicians treat these subjects. And the reason why this was used for astronomers was, if you looked at astronomy in the past, the amount of data which we had was absolutely less. It was whatever people could see with the naked eye, they tried to map it in the sky on a paper. Then they would see through a telescope and make maps of what they saw. Like you have these Herschel's images of the nebulae which he saw. Some of them are galaxies and some are star-forming regions. Then you have Galileo's drawings of moons of Jupiter. He saw them through the telescope and plotted them. And here's again some images which they sketched and drew. On the right-hand corner, we have images done by Galileo of Venus and the phases of Venus and so on. And right in the center, we again have image of the sun with its sunspots. So the data was less, and what we have today is tremendous amount of data. If you see Pleiades constellation, which we see, or you can see my mouse, this was the Pleiades constellation where people saw 7 objects, or then they saw 14 of them and so on. But today we see this Pleiades, and more than 1,000 members have been statistically, we realize that they had, at least 1,000 confirmed members of this constellation. So the data from each object, each cluster has grown tremendously. We have images of the sun with tremendous amount of information and energy, which keeps coming from various observatories like the Aditya or the SOHO and so on. We have galaxies being imaged in various wave bands, and we have these big data cubes where you have information in various wave bands, right from 0.65 microns to 1.64, 1.84, and so on. So astronomy has grown from data poor to a data-rich science. Today we live in an era of multiple wavelength astronomy, various ground-based and space surveys ranging from gamma rays, X-rays, ultraviolets, optical and infrared to radio bands has brought astronomy into the big data era. Astronomical data is already amounting to petabytes and exabytes, increasing with the advent of new instruments. And hence, astronomy has evolved from hypothesis-driven data poor to a data-rich science. And this is where virtual observatories sets in and gives a stage for how we handle it, how we handle this tremendous amount of data. So what is big data? Different definitions of the characteristics of big data are there. Kirk Bond put forward 10 V's to it. Big in the sense of volume, variety, velocity, veracity, validity, value, variability, venue, vocabulary, and vagueness. We will consider only 4 of these 10 V's in the context of astronomy, namely volume, variety, velocity, and value. So when it comes to talking about the volume of data we are getting in astronomy now, we get about 5,000 terabytes of data, which was required to compose this first image of the black hole using the Event Horizon Telescope, right, which was found at the center of M87 galaxy. And the data which amounted to is 500 terabytes of it, which requires, 44 years to upload at standard internet connections and about 22 years to download. So today we are learning techniques of handling high amounts of data in different ways. We do computation directly on the cloud, log on and do it. The volume, if you look at the volume of data which is flowing in, we have these sky surveys like we have the DPOS, the Palomar Digital Sky Survey, which amounts to 3 terabytes of data. 2MAS, the 2 micron all sky survey, about 10 terabytes. Galax, the Galaxy Evolution Explorer to 30 terabytes. SDSS to 40 terabytes. Vera Rubin Observatory, it's expected we'll be getting from 14 terabytes per day to 50 petabytes per year. And LSST, the last synoptic skies telescope, 200 petabytes. And the SK, the square kilometer error, to 5 terabytes per second, amounting to 400 petabytes per year. And it's expected to get approximately 4.6 exabytes of data. So we are living in a time of where astronomy data is, in terms of volume, is tremendous. Coming to looking at the variety, we have images, we have spectra, we have time series data, we have simulation data. The data is saved in catalogs or in databases. The data from sources are made available in different formats. Each data item often has more than thousands of features. Data has many data types, structured, semi-structured, unstructured, and mixed. Coming to the velocity in the terms of the amount of which is created and which has to be downloaded or uploaded, in the context, the speed of producing, transmitting, and analyzing data, the LSST expects it to find 1,000 new supernovae each night for 10 years, which implies that at least 10 to 100,000 alerts will be requested, right? So you have to send these alerts at tremendous velocity. It has to reach people who are hunting these supernovae, looking at them and studying them, to reach them very fast. And the value, it characterizes the high value of astronomy data. In astronomy, to discover a rare, unexpected events and new objects or new phenomena, and the discovery of new distribution trends or laws is of great value. So these are the 4 values I was mentioning about in terms of astronomy. And there are various astronomy tasks, like you have spectral classifications of stars, galaxies, quasars, supernovae. We have photometric classifications of, again, stars, galaxies, quasars, and so on. Morphological classifications of galaxies, solar activities, right? So we require artificial neural networks, we require support vector machines, we require learning vector quantization, decision trees, random forests, nearest neighbor methods, and all kinds of machine learning tools, AI and machine learning tools, which we are using for market. They are very much used even for astronomy, and they are very essential. And this is required for classification of galaxies, quasars, stars, supernovae, and so on. Coming to photometric redshifts, which we have redshifts of galaxies, we have redshifts of quasars, which give us an understanding of distance of these objects from us and giving us an understanding of the vastness of the universe and the expansion rates. We have stellar physical parameters like Ferris-to-hydrogen ratio and temperature and so on. Again, we require artificial neural networks and vector regression, decision trees, random forests, least square regressions, and so on and so forth. And all this is for regression analysis, setting up relations, linear or non-linear relations between phenomena and so on. So we have a lot of data mining tasks like clustering, outlier detections, which is again very important, time series analysis. And for this, we require uh, uh, principal component analysis. We have DB scan method, k-means, optics, and so on. And when we are dealing with so much of data which is coming in from all the multi-wavelength data coming from millions of objects, from various observatories, from virtual observatories, from simulations, from ground-based observatories, it has become very important to have more people study it and to make some standards as to how this data should be collected, how it should be distributed, and how it can be analyzed. And to understand this complex astrophysical phenomena, the answer to this, the issues of living in a exponential world where the data is flowing in at tremendous rates, the answer to that comes from from virtual observatories. Yeah. So what are virtual observatories? Virtual there's an IVOA, International Virtual Observatory Alliance, and this was formed in June 2002. Presently, this IVOA comprises of 17 VO projects, which has VO Australia, VO India, VO Canada, Europe, VO, and then so on. This icon on the left side will show you the various 17 countries which are participating in that. And VO India is also a part of this consortium. And the mission of this Virtual Observatory Alliance is to facilitate the international coordination and collaboration necessary for the development and deployment of the tools, systems, and organizational structures necessary to enable the international utilization of astronomical archives as an integrated and interoperating virtual observatory, right? So the basic idea is IVO VOA organization chart is you have the media group, you have the executive committee, which has two wings to it, media and the committee of science priorities. Then we have the technical coordination group and standards and process committee. The technical coordination group has two subgroups in it, the working group and the interest group. The working group looks at the applications, data access layers, data models, grid and web services, registry, and semantics. And the interest group are the data curators and preservations for education, for theory, to study the time domain astronomy, for operations, to discover new phenomena, to study, understand astronomy better, discovery, and to study the solar system and so on. Okay, so the basic idea behind IVO is there's tremendous amount of data which is flowing in. So they are defining protocols as to how data should be shared. How data, because if you make an observation from any observatory, it has to go through a pipeline. One has to know the instrument where it has been taken from, on what date and what location it has been taken from. And you have to know, say, of that camera, the CCD which we are using, what is the bad pixel marks and what are if there are some errors in the sensitivity of the CCD and so on. So the data has to be processed. The raw data has to go through a pipeline and given into a form where the user can use it. So this International Virtual Observatory Alliance is defining protocols which say how images have to be shared. It has to go through at each observatory, at each site, they have to do the pre-processing, and what is made available on the internet through their sites is processed data. Okay. Otherwise, you need to have a lot of innovation. Other than that, they have defined certain protocols, and it's decided that the images, astronomical data, has to be shared in FITS format. FITS stands for Flexible Image Transport System. I'll come to it in detail further. But so this Virtual Observatory Alliance decides the protocols, the rules, and standards in which the data has to be shared. It has to be made accessible to all, and it is not the proprietary of any individual, but after a certain time, it is made available for everyone. Yeah. So because a tremendous amount of money is being spent in creating these facilities, say the James Webb Telescope or the Hubble Space Telescope or the Chandra Telescope, or even the ground-based telescopes. When you set up an observatory, there's tremendous amount of data, money which goes in, and the principal investigator might make observations for a specific thing, but after they have analyzed and used the data they had got from the observations, it has become mandatory to make it available after a certain time. So depending on which observatory, which uh, telescope we are talking about, they have their own different periods after which the data is made available. And it has to be made available in a certain way which is accessible to all. Then, and also the Virtual Observatory Alliance has built up certain VO tools which allow us to analyze and interpret this data, right? So coming to even looking at the astronomy data, we have images, we have catalogs, we have spectra, we have polarization data, and so on. So what are images? Basically, images are these two-dimensional arrays. So the CCDs they stand for charge coupled devices, and they are these picture elements which, when light falls onto it, it records certain number of photons. So each pixel records certain number of photons, and from which we construct these images. And all the CCD images, if we look at, are black and white because they are only recording the numbers. So mathematically, you can see them as only a matrix with each square keeping a certain number. The number signifies amount of light which has entered and recorded in that. And by taking images in different wavebands, like in red or in blue, then you can construct these colored images. So you have these RGB images, and they use artificial colors with which you can construct the images. So all the beautiful colored images which we see coming from Hubble space or James Webb or Chandra, the color is done later artificially related to the wavelength. So you need to have more than one filter through which you observe an object, and from B minus V, blue and violet, or from two filters you can construct the actual color. Then these basics, you can have point sources like the stars and all. They come as point sources, while galaxies are extended objects, or star forming regions are extended objects. And these are the two people, Willard S. Boyle and George E. Smith. They are the inventors of the charged coupled devices. Those charged coupled devices, or CCD, are nothing but these digital cameras which we use. But the ones which we use in astronomy are much more sensitive and much more sophisticated than the digital cameras which we have in our cell phones. So the color filter array for arranging the RGB color filters on square grids of photosensors, the filter patterns is 50% of green, 25 of red, and 25 of blue. And with these, you construct these, you take through different filters, and as the light comes in through different filters, to record different intensities, and by combining them, we can get the actual. We construct these beautiful colored images, right? So FITS is one way of has become a standard of relaying, distributing astronomy data, astronomy images, and FIT stands for Flexible Image Transport System. It is an open standard defining the digital file format used for storage, transmission, and processing of data. And FITS, it not only gives you the image of an object, but it also uh, gives the spatial calibration, the photogrammetric information. It gives the metadata of the whole thing, and I will show you in later how you have different layers in these FITS format. One is which has the header file, which keeps information about when that image was taken, what was the temperature of the CCD, how many minutes exposure was it, and in which filter, what was the filter use, and so on and so forth. So it is not only the picture, the image, photograph, but rather FITS also encompasses into it various different information regarding this picture. So when we are reading a FITS image, you have to read through some in a specific way, either through virtual observatory tools like DS9 or SOAR. These days, this thing is being done very efficiently through Python programming. And these days, you have not. These are called data cubes. FITS comes in is also often used to store non-image data such as spectra, photon list. It has data cubes on it. In the same image, same file, you have different slices in it, and each slice will have, say, image in X-ray, image in infrared exposure, image in various wavebands. So these are, okay. And by looking at and by data, by looking at different exposures and by cleaning these data CCD images, we can improve the quality of what we see. The important and interesting part of CCD images is the response to light is linear. So if you expose a certain amount of light for 5 seconds, or do it for 10 seconds, there's a direct linear response to it. Point number one. Second important thing of CCD images is dynamic range is very large. It can record very faint light as well as it can record very bright light. While photographic plates, which were used earlier, there's a limit. If you expose it to very bright light, after certain, it starts saturating, right? So you can't expose it to too bright a light. So the advantage of this is if I am taking, say, an image of an object for about, say, 30 seconds, and there's a bright object there, if I expose it for too long, then the bright object would collect so much of photons that it can spill over from the pixels and start bleeding over to the other areas. While if I take a very short exposure, then it will not record the faint objects. So since the CCD images response is linear, we can take many short exposures. For example, if I take, instead of 1 30-second exposure, I take 6 5-second exposures and stack them up and add them up. It will be equivalent to taking a 30-second exposure, and the chance of overspilling or saturation of certain pixels doesn't come in, right? And then since it's a digital, it's basically a matrix, an array of numbers. You can add, like two matrices get added up. You can subtract the background. You can take images of the background sky. You can take the images of a uniformly lit sky and see the response of the CCD. And there is a process by which you can go from an image where you can't see objects to a very clear image with the right intensities and so on. And this is how we can construct such beautiful images from this data. Sure. So we have this spectra data and yeah. So these are the data cubes where you have different slices. We have the same object, and these fixed images, you can view it as a data slice, where each slice is an image of the same object in different filters. And this is bundled up and given to us as a single object. And from one fixed image, you can construct in different wavebands and see the different phenomena which is going on in different regions of a certain galaxy or a certain cloud. Then apart from that, we have these catalogs of data, yeah, where you have, say, for example, the name of the cluster, we have the right ascension declination, we have galactic longitude, galactic latitude, and radius, and the proper motion in RA, proper motion in DEC. So we get these kind of catalogs of each object which we have. Apart from that, we have time series data at different time steps. We are looking at measuring certain light intensity and seeing how a star, a variable star or an object is varying in brightness or changing its, right? So you have time series data. So virtual observatories have developed various tools and they are made available for anyone to access this data, to visualize this data, to analyze these catalogs using different tools. For example, we have DS9, which is the visualizing tool. You have TopCat, which allows us to read these catalogs and make plots. Then there's various programming languages like Python and various modules in Python, which allows us to analyze this data. So the Virtual Observatories Consortium has decided how this metadata, the description has to be given of the data, the images, what kind of telescope is being used, what was the exposure time, and all the details have to be supplied. And similarly for spectra and for simulations. So they have defined the protocols and defined the rules as to how it has to be distributed. So how do we access this data? We have the CDS, which is Strasbourg Astronomical Data Center. So there are various catalogs there, which collects and distributes astronomical data catalogs related to observations of stars and galaxies, other galactic and extragalactic objects, and solar system bodies, and so on, even atomic data. So then we have Simbad. Simbad is where you can access these astronomical databases, again handled by this SDSS. And as you see, as of 7th of October 2025, Simbad contains 20 million odd objects. It has 69 million identifiers. It has 4,500,000 bibliographic references and so many citations and so on. So this is a tremendous amount of information which is available on SDSS, which you can access through Simbad. I will show you how you access those. And there is a smaller, or you look below, the statistics which it shows. If you see 11 December 2021, just 4 years from now, or less than 4 years from now, this is 2021, and the one on top is for 2025. You see, in 2021 December, we have 12,995,000 and odd objects, while now we have 20 million, right? So the amount of data and these objects is growing tremendously at a very high pace. So then we have these Visio services. Visio services are query services for catalogs. You have catalogs and you have bibliography of the data which has been collected, right? A person observes and gives out the data in terms of tables. See, we have seen an example of one table where you had the object name, you have the right ascension declination, or the galactic longitude latitude. What is the proper motion? What is the metallicity? Proper motion area, proper motion index, metallicity, and so on and so forth. So you have these large amounts of databases, data frames with multiple columns having tremendous amount of information for thousands and millions of objects. So all these observations from all over the world, from the ground-based surveys to sky surveys, from telescopes on the ground to the observatories, the celestial observatories, all of this data are being stored in a standardized form, and there are standardized ways of accessing this data. So this Visio services is the query service. How do you query? If I want to say get data on M31, and I want to get data in which is got by SDSS, and then get from the Thomas or from which survey we are using, we can query, we can specify which waveband we are interested in, and so on. So these Visio services have a query services. They have made very simple forms where you can basically click boxes and decide how many columns, which columns you want to download and how much of data you want it. So it is for cross-matching across catalogs, the national extragalactic objects, the Simbad objects, right? So this is a query service which allows us to get catalogs as well as bibliography. Bibliography tells you what kind of work has been done, what results have been done, which papers have published work on that, so you can get an access on that too. So Visio provides the most complete library of published astronomical catalogs, tables, and associated data with verified and enriched data accessible via multiple interfaces. They are query tools which allow the user to select relevant data tables and to extract and format records matching the given criteria. You can specify what criteria you want and you download it, and then there are tools with which you can match different catalogs and so on. And currently, there are 26,721 catalogs available in this Visio services. Then another very beautiful virtual observatory tool is this Aladdin. It is an interactive software sky atlas, allowing the user to visualize digitized astronomical images and superimpose images entries from astronomical catalogs. So I can now go into. I can show how to access these things, and yeah. So I hope you can see my screen.
Yes,
So
sir.
so say, for example, we have these Vizier, and you just search for Vizier catalogs, and you have this interface, right? And you can you can say find catalogs among 26,725 available ones. And here you can specify what you are looking for and in which wavelength you are looking for and which mission and which astronomy and so on. And it gives you, depending on how fast is your, right? So see, M51 I searched for, and it is giving me all these catalogs, which says it's a time series one, and ABJ has published on this. You can read on that. You can, uh, galaxies in UMA cluster complex. Yeah, so you have all these things. You can click on them and you can start downloading it. Okay. So you have this Vizier. Similarly, you have, and there's interoperability. They all talk to each other. You can, so I'll show you each one of it shortly, and then you can, if you go to Simbad, yeah, so Simbad is this astronomical database, again run by CDS Strasbourg. And again, you have a basic search by identifier, by coordinates, by criteria. You can set a criteria with which you can search. Yeah, so you have to try this out yourself, and you'll see how easy it is. And you can, yes, the basic query is like this. Again, if now I say M31 and I search Simbad, so it says M31 is a globular cluster, and it is loading this image here on the side, and it shows you the various things. Okay, the different articles in which people have published on this in MNRAs. This you can click any on your of this, and it will take you to that paper which says what has been done and what has not been done. Coming to Aladdin, Aladdin is the Sky Atlas, where you can download Aladdin for your desktop. Okay, or you can have a preview light on your screen itself. And Aladdin is for you to visualize this data. You can see the images. So target name is specify M51, suppose I say, and I can specify. Yeah, so here I have M50, the Whirlpool Galaxy, right? And you can have different filters. If you see on this, you can stack up. You can put different layers. One is the DSS image. You can add to it in Furby color, right? So you can have different layers on it, and the same you can stack up the same ones. So the radio observations of this, the optical and different wave bands and so on, and this is a beautiful tool for you to do visualization and so on. Okay, so you have all these different speeds, whichever one you choose, you can choose, and yeah, so you're seeing them in different wave bands, different data got from different telescopes and so on. The same thing can be downloaded, and this will come as depending on you are using Windows or you are using Linux, you are using Windows with Java or the MSI installer, or you are using a Mac, you can download uh, Aladdin and you can do the same thing, right? So what we saw was through the web browser, which is the preview. This is the light version. The other one is the right. Similarly, yeah. So these are tremendous ways of accessing catalogs, data, and all these are made available for free. I have listed here some of the statistical packages which can be used to analyze. So see, now that we are living in times of astronomy with tremendous amounts of data coming in, we have to use statistics to make sense out of it. And we require all kinds of tools to do that. So there are certain proprietary statistical packages like SPSS, Statistica, Maple, MATLAB, Mathematica, and all, but you'll have to pay for them. There are certain public domain ones like Bright Stats, CPS Pro, MANUU, REMA, and so on. And then we also have the open source ones like PSPP, which is a free software replacement for SPSS. We have R, which is a very powerful statistical package, also an open source one, freely available. We have SlimFit and SOFA statistical labs, and not to forget Python. Python is now replacing all these tools and so on. It's a very powerful way of handling all kinds of databases, all kinds of big data, and especially so for astronomers and so on. So apart from these open source like R, which is a very powerful package, we have virtual observatory tools, VO tools, in which we have VO tables, VO plot, TopCat, Mirage. So VO tables is to display tables and to analyze the tables. VO plot is to plot from these catalogs. TopCat is again a very powerful. We can have a whole session on how TopCat can be used to handle data from catalogs, not just astronomical data, but any data. How to make plots, polar plots, 2-dimensional, 3-dimensional plots, to turn them around and see from different angles. Then to image display, we have Aladdin, Oasis, and DS9 and so on. And for spectrum display and analysis, we have VOSpec and SpecView. All these have been developed by the virtual observatories and made freely available. But now we are slowly moving towards more and more towards Python and AstroPy, which is a very powerful way of handling. So VOStat, some glimpses I will show you. This is a web service and also standalone version. You can download it on your system and use it, or use it directly from the browser. So we have this VOStat. This was developed by Virtual Observatories India, where it can see different categories. You have 26 different tests in it. It has some basic tests that group together. Yeah, so you can choose what tests you want to run, whether it is an ANOVA, whether you want to do pair plots, you want to do what kind of, right? So they have 26 different T tests, F tests, various tests, 26 different type of tests, and so on. Then you have the user can see the source files along with the data. This so that you can select which columns, right? So this is giving you the source file, and this is basically to make the whole thing data transparent. You can work at the data at very fundamental basic level, or you can use through these interface where you can see that you can just by click of the button you can upload the files right from the net or from the system and do various statistical tests by just clicking like tests. You have K-sample tests, exploratory tools. Just by clicking these, you can do these tests. Then it has a lot of help pages which tell you how to and also gives you the basics, the fundamentals of this. Right. So all these have been developed by Virtual Observatories India, and you can output your results into whichever format you like. And this output can also be used in other programming languages or programming tools like the R or Python and so on. Right? So VO stats also allows you to make histograms or box plots or pair plots, quartile plots, and all kinds of sophisticated statistical plots which you require can be done. You can do that with your data. You can do HR diagrams, you can, and then there is an interoperability between Aladdin and the plot. You select an object in Aladdin, and in the viewer plot it gets marked, right? So they talk to each other, and these are extremely powerful tools where you can analyze and study these details. And all these tools are made freely available, easily downloadable, and this is making astronomy making it democratic. At a time when we are living in a time when everything you have to pay for doing everything, for every service you get, here is the whole community of people who is sharing data, sharing resources, sharing tools to analyze data free of cost to each other. Right? Similarly, you have virtual observatory VOCAT, which is used to look at the catalogs, and again, you are looking at the catalogs and the Aladdin and VO plot, and there's an interoperability between them. The Simbad page, the Aladdin, and VO, right? So there's the beauty of this. And as you use them, you'll get more and more familiar with this. And what virtual observatory today is, it has really matured. And it has made data accessible and available to everyone, right? Irrespective of where we are, only thing you need is a internet connection. There was a time when good institutes were those where you had an access to data or to the facilities, to observatories, to so on. But today we are living in times where you can be sitting in the remotest of the part of the world, and if you have access to internet, you can download data of the best quality taken from from facilities where crores, millions of dollars and rupees have been spent to construct them, and it is being made freely available to all, irrespective of your demography, your location, your nationality, your right. Only thing is you have to have desire to work on a certain thing, right? And also the tools have really grown. They are very powerful tools, also made available to everyone. And all this is promising us a new and exciting era in astrophysics. So I think I can stop for a while now. I can stop for a while now and take questions if there are any.
Yeah,
Or
thank
I
you.
can also, yeah.
So
Yeah,
I,
so I'll stop sharing. Yes.
I'll bring the questions to you, sir. The first question is, what can a person do as a university student in second year to be better at astronomy to compete in Olympiads? Also, please let us know more and more about similar things like Olympiads for university students who aren't now in high school anymore.
Yeah, so unfortunately, these Olympiads that they are Olympiads done at two levels. One is under 9, 10 standards and 11, 12. Right? We don't have all astronomy Olympiads or math Olympiad at BSc level. So as far as I know, because we have been a part of training astronomy Olympiad students, I have gone as team leader to international events too, where Indian students do extremely well. Very often we are at the top. So Indian students do extremely well, and Homi Bhabha Center in Bombay is the seat for that, where a lot of people from all around this country come and we mentor them. There are people who come from from Ayuka, Priya ma'am and me also go there to, right? But there are no Olympiads for BSc students. They are till your 12th standard. But yes, being in the first year, second year, graduation, you can do good, serious astronomy if you like. And the best way to do that is to identify a mentor, try to find a person who can mentor you. We have mentored many people where we have mentored children from school level all the way till research scholars, where we see what is their interest and their strength, because some are very good at programming, some are good at uh, observations and so on. So now you have a lot of data available, and you can get down to working. It can be data from exoplanet database, it can be data from James Webb telescope. All this data is made available. Yeah, you have tremendous amount of data, Gaia data available on our right. So we are getting a complete new understanding about our Milky Way galaxy, about how it is constructed. You know what our textbook said 20 years back, and what we understand our Milky Way as today is something absolutely different. Right? So this data is available, and you can participate in. And then there are certain telescopes like the LCO, where you can even schedule your observations, make your own observations, and do data. So you can get your first-hand observatories from remote robotic telescopes and get data, or you can get first-hand exceptionally good data from these Vizier catalogs and so on, where you can get data from Hubble Space Telescope, from Chandra, from Gaia, from so on, and do some science cases and do it. So yeah, so you needn't bother about astronomy, Olympiads, and so on. That is just to inculcate students into getting in. Now, when you are in BSc, you can get into more and more serious work.
Right, sir. Thank you. Thank you, sir. The next question is, how much is machine learning being used in astronomy? And what could be the future for us as young physicists in the field of astrosciences? I want to know this because there is a lot of buzz of AI and ML these days.
Yeah, exactly. So, see, we are living in times of AI. We are living in times where there's tremendous amount of data which is flowing in. And when you have so much of data, you need machines to analyze it. It's not humanly possible for us to sit down. Like there was a time when we used to add up rows of numbers, then add them and multiply them, use log tables, and it was not very long back till the time calculators were discovered. And then for the new generation, maybe everything, you have not gone through that, but we have seen an era where we were not allowed to use calculators in universities and colleges. Then calculators was allowed, then computers were not used slowly, right? So now we have tremendous amount of data coming in, and it has become essential to use machine learning tools and AI to handle this, right? So there's no going back from that. And same is the case with astronomy. Astronomy also, we have seen there are so many surveys, so many catalogs which I've shown you, tremendous amount of data. In each catalog, each table which you download, there can be millions of objects there. And to make sense out of it, we require machine learning techniques. So what we are doing now is we are giving our research scholars who are doing PhD with us in astronomy, we are encouraging them to use these machine learning tools to analyze this data. So, like for example, you have star clusters and you want to define which are members of that. You take an image of some region of the sky and you image all objects in the foreground as well as in background. And there was the traditional ways of deciding which belong to this cluster and which are non-members. So there are certain techniques, but now we are encouraging our students to use machine learning techniques to do that. And the reason why we are doing it is it will develop their skills of using machine learning and AI. And this will make them more employable in the, so they can use these techniques to do astronomy. We'll be most happy if they can do that. But even if they don't get a job in a university or a research institute or a position, they can use the same skills to handle a tremendous amount of data which is lying with big companies, which are Amazon or Google or, right? So data today empowers people. And if you are looking at big companies, why are they big? Because they have data, access to data, and tools to analyze and make sense of the data. And there's so much of data available that you cannot do it but use machine learning tools and AI tools. So you have to get equipped with it. And it is being very much used in astronomy. The trend is changing from what it was even 5 years back when people when we were trying to, one of PMM student was using machine learning techniques for star cluster analysis. We were working together. People were they were wondering how true it is, how good it is, and how accurate it is. But in these 3, 4, 5 years, the whole attitude is changing. There are many, many more people using machine learning tools, machine learning in astronomy, in astrophysics. Yeah.
Definitely, sir. AI and machine learning is really, really important. So the next question coming up is, as so many observatories around the world share the data through these virtual networks, how do scientists make sure the information stays accurate and well calibrated across different systems?
Yeah, so that's a very important thing. And that's the role of the Virtual Observatories Consortium. They have defined certain rules, certain protocols, certain ways how data has to be shared. And it's a responsibility of these individual observatories to share it specifically in those formats and in that form. So they have to be. And if somebody is, you can't upload your data on Vizier and so on yourself. It has to go through a mechanism where it is done, and they upload it when they are sure that the data is of good quality and in the format and way it's supposed to be. Right. So the data which you'll get from SG is this Salzburg center. These are very well reviewed and analyzed and seen. They stick to the protocols. So the virtual observatory consortiums are held regularly all around the world. We were attending one recently in Washington, D.C., and there where people discuss uh, how they have to improve the standards, how the data has to be, as technology is changing, the kind of data coming in is different. What we thought 10 years back is different from what we understand today. So there's a continuous updation of how data has to be preserved, how it has to be archived, how it has to be shared, how it can be queried and accessed by everyone, right? So there are people who are sitting behind and working, very serious and very capable people.
Definitely, sir. So Yuvraj is asking that he was studying some pictures he took from an observatory in Tenerife and saw the same effect of linear brightness that increases with exposure on them. How things are relating in catalogs, does the NASA Exoplanet Archive qualify as a catalog?
Yeah. The NASA, we have NASA exoplanet archives which are available, and you can access it's tremendous. It's very good information, very good data, which our students are using, and it does qualify in that. Yeah, without a doubt.
Okay. Bala Venkat asks you, Can the data available through SIMBA for the object metadata and Aladdin for image retrieval from sky surveys be used to train machine learning models?
Of course, yes. That's been done. One thing is you can download this tremendous amount of data and you can train machines yourself. It can be done. It is being done. Yeah. Even SDSS data, you have Sloan Digital Sky Survey, which has tremendous amount of uh, data of various galaxies. So earlier they were using human beings. They were training humans to classify the galaxies in different components, right? Initially, there were certain training sets where you could see a picture and you said it was spiral, then spiral with a bar, or an irregular, or an or elliptical SA, or SB, or SC. So initially, you can go through those training lessons where you get trained, and then you start. They were using humans all around the world to bin this data rather, right? So a lot of people from different places got in. Even some of our MSc students, and if you do say for more than 100 galaxies, then your name gets registered there. They give
Yeah.
you say that you have been so many. Then it goes to the second filter and so on. Now the same thing is being done by machine learning. And there are different machine learning techniques of looking at, say, morphology of galaxies and so on, and classifying them, or stellar spectra, right? Earlier, there were humans who could look at the spectra and say it is O-type star, B-type, OB, and so on and so forth. But now they are run through these machine learning algorithms, and they are much more efficient, much more faster, and probably much more accurate than human beings can be. Yeah. So this astronomy databases are being used to train the sets and to do this. Yeah.
So even I have done the galaxy classification thing from the project from Ayuka, as well as the project from National Observatory of Japan.
Yes.
The next question coming up. What are the future goals and expected advancements for the virtual observatory in the next decade?
Oh, that's a tough question, because as technology changes, we don't know how and where the technology goes. And what I see with virtual observatories is they are going to, like I said, they constantly have meetings, interoperability meetings, where they talk about the issues and the problems they are having, and they are constantly working for building new tools, new techniques, and so on to handle these things. So they'll keep evolving in time to handle the issues as they come. So what's going to come? We'll have more sensitive cameras, more sensitive ways. See, earlier people saw and they studied astronomy. Then they started using telescopes, but basically they were looking through the eyepiece and trying to understand. Then they attached spectroscopes and so on to spectra of individual objects and did it. Then now you can have fiber optics, where you can take spectra of thousands of stars in that field at the same time. Rather than looking at one star at a time, you put these fiber cables and take spectra at one go. So you get spectra of all the stars in a cluster in a very efficient way. So as time progresses, the techniques of handling the data and the amount of data which is coming in, that keeps changing, and new and better ways will keep coming, right? So yeah, it's an interesting question, but we can't predict. At least I can't predict where.
I think so. The technology is advancing really fast, and it's
Tremendous,
changing day
yes.
by day.
Yes.
Yeah. The
In
next question.
1990s, I remember when 93 I finished my PhD and email was limping into the
Yeah.
services. And you had to, dial up and some mails would pop in and pop out. And then even internet was very primitive. There were some very few search engines with which you could search for some information. But within a few days and years, it has tremendously increased. Secondly, now the number of satellites which are orbiting our Earth, which are observing the Earth or which are looking at the space, they have grown tremendously. The amount of data coming in is tremendous. Hence, the techniques of handling is changing. You have machine learning techniques and clustering and all kinds of networks and all kinds of, and they are being used in astronomy very seriously because we have no way out otherwise. Yeah.
So the next question is completing a course on Python per se enough for someone who doesn't have continued active presence in the coding field? What would you suggest we can do better to excel in Python?
Yeah, so what I would say is Python, you can't sit down and learn all of Python, right? You have to tailor make, your knowledge in Python for your requirement. So you have to define what your problem is. And depending on what you are looking at, just handle that. That's what we are doing with our students. We are getting them right into the middle of Python by actually getting the data, giving some very fundamental things about Python, and then you teach them AstroPy, which is a very good package for astronomy people, where you can make conversion from longitude to alt-azimuth system, from galactic to this, from light years to parsecs, and so on. And using AstroPy, you can give sky coordinates and download data. In fact, I wanted to show how you can even access Vizier catalogs and Simba through Python notebook. So, so specifically, you can learn that module, those things which are required for your work, and as you work, continue doing it to start becoming an expert in that area, and you start learning it. So, a very basic knowledge of Python, I say, is sufficient. Now you have to get down to actually downloading data of whatever thing you are interested in. It could be galaxy morphology, it could be star clusters, it could be exoplanets or light curves of binaries or whatever, and specifically build up your expertise around that, right? So, and it is very simple to do that. And these are just tools. These are tools. The actual thing which understanding what the results give you, your interpretation is what is important. That's where the human thing comes in, right? So these are basically they are just making your life simpler, nothing more. There's no magic going on there.
Definitely, sir. So the next question is coming up from Shivam. Shivam, kindly unmute yourself. Shivam, kindly unmute yourself.
Hello, I'm audible.
Yeah.
Yeah, yes.
So currently I'm in my second year doing my BSc, and I'm already learning libraries like MATLAB and Astropy, and also doing some basic projects to get my hands on. So I want to research more about early universe neutrinos and the origin of early galaxies. Sir, what will you suggest me? What projects can I do to improve my knowledge, and what should I do to proceed in this endeavor?
Yeah. So one thing I would suggest is you get attached to somebody who's studying those areas, right? And somebody who's ready to help you. So Priya and me, we are very open to encouraging students, and many people have done different kinds of work. They have worked on galaxy morphology. They have worked on clusters of galaxies and various aspects. So you can take down my email ID and phone number. Ma'am can probably provide that, or I can share it in the chat here. And you get in contact with us, and one-to-one we'll find out what your basic interests are and who's the best person who can do that. It's not only we two who are ready to help. There are similar people in NCRA. There's a lady called Shoshan Konar, very good. She works on compact objects, very open to helping students. So in these online sessions which we have had, some people get attached and they have even published papers with her and with us. Similarly, we have Desh, who was in RRI earlier and now he's in Ayuka. Extremely helpful, very open person who's ready to help, and he's a radio astronomer and of very high caliber, very good person and very helpful. So if you want, I can share my...
Definitely, sir. So
Okay,
please.
sir.
Yeah, so then one-to-one you can specify exactly, and once we start interacting, we'll get to know what your basic interests are and how to go about. So this is my email ID, and this is Priya's email ID, and phone numbers. I'm sure you have. So we have converted many. This is mine, and this is Priya ma'am's. So some engineering students who are even working in TCS, Tata Consultancy Service, they are now full-fledged astrophysicists. They came to us, they were interested in astronomy, they worked on different aspects of it. One went to Rochester, did a PhD, worked in Arecibo, worked in GMRT. She's a brilliant person. Another Renuka is another such person. Karthik Reddy is yet another. They're all engineers who who have left engineering, their lucrative jobs, and they're doing research in astrophysics now.
Okay, thanks a lot.
Yeah. So you get in touch with us and we'll fine tune your problem and tell you how to access the data and whom to contact and how to go about. Okay?
Okay, sir. Thank you.
Yeah.
So the next question is coming from Akash Kumar.
Yeah.
Akash.
Yes, Akash, hello.
Good evening, sir.
Good evening.
So first of all, thank you so much for such a fascinating session. I really liked how you explained the idea of making astronomy more open and accessible for everyone through visual and virtual observatories. My question is, since these observatories generate massive amount of data every day, do you think the combination of artificial intelligence and virtual observatories platforms could it help us detect new cosmic phenomena faster, maybe even before scientists notice them manually?
Of course, yes. So if we are using the AI tools well and the data in a smart way, you should be able to do that. Yeah. So these AI tools are extremely powerful. See, you have to use it judiciously. You should not use AI as a black box because it can give you any results. So obviously, if you use it smartly, you can, because the data is tremendous and it's not humanly possible for you to sit down and look at it minutely. Only way you can do it is by using some smart techniques of doing it. And AI is basically, that's what it does. Artificial intelligence these are algorithms which are made by human beings. It's not really speaking artificial. Yeah. So in a way, so by making these tools, by making these, using these techniques and tools, yes, we should be able to discover phenomena and things. And like even that image of the black hole, which the first image which came out, it is a synthesized image. It's used by simulations and so on, right? You can't photograph a black hole. Yeah, we have never had images. And the image of the donut which you see is actually composed image from
Yes,
data you understand, interpret it, and then you reconstruct using imaging tools, right? So
yes, sir.
AI and machine learning and various things are being used. Yeah, yeah. In fact, there is one very simple problem which has lasted for over 400 years. It is called the three-body problem. Yes,
Yes,
right
sir.
from Newton to 20th century, all great mathematicians at some stage studied it. Newton, Jacobi, Lagrange, Hamilton, Poincaré. It's called the three-body problem, which is basically if you have three masses, say Earth, Sun, and Moon system, you know their
Yes, sir.
masses, and you know their positions and velocities. Can you predict how will they move? Can you find a general solution to this three-body problem? Sounds extremely simple, right? But if you have two bodies, you can write equations of motion and solve them. But if you have three bodies, you cannot find a general closed form solution, right? And trying to solve this has led to development of a lot of mathematics, perturbation theory, stability theory, calm theory, and so on. And so you can't find a general solution which has been proved that you cannot find. So you can find analytical solutions, quasi periodic solutions, and so on. Interesting thing is they are using machine learning. They are training machines to solve this three-body problem, and they are much more efficient than the semi-analytical and analytical techniques which we have been doing. So a problem which was survived for
Yes, yes.
400 years, the machine learning is being used to solve that problem. And it is giving pretty good. So you change initial conditions and the machine generates and says, this is how finally they land up, right? And you can't do it with the equations. You cannot solve those equations because small changes in initial conditions lead to chaotic orbits or non-chaotic. It's a very interesting problem. Yeah. So, and machine learning is being used to do that. Okay.
Yes, yes. Thank you so much, sir. That explanation truly broadened my perspective. Combining AI and virtual observing sound like a future smart astronomy. I will definitely explore this area further. Thank you so much, sir.
Good, good. Yeah. Very good.
Sir, Yuvraj has another question. How can someone in geology contribute to astronomy and astrophysics? Can we as geologists go into astronomy further in future, or at least somewhat related of a field?
Yeah, geology and astronomy are, I think, pretty close in some sense. One is looking down on yourself, and one is looking up.
Up.
But finally, we are all trying to understand how was, say, we created, how was this Earth created, and so astronomers try to find answers outside. You see other planets in preparation, being formed, evolving, different stages of evolution, seeing how the pattern evolves, how elements are created, how are they, right? So basically, astronomy answers those questions that all these elements are, they are furnace inside stars, and some are furnace when in supernovae when they explode. And when does a star have a planetary system around it? So it has to have this debris from some supernova there to make it. So yes, they are complementary to each other, and knowledge of one and the other can always help to understand uh, how the universe was created and how is it going to end up. Yeah.
Right, sir.
And I think every child at some stage is a geologist and an astronomer. Children look up at the skies and they constantly ask questions. And most of the time, when the parents or the peers don't have right answers, they tell them that these are souls of dead people and this and that and kill their curiosity. And same, every child goes through a stage where they collect stones. They pick
Yeah.
up stones and they say, this is shiny, this is black, this is brown. And if the parents are welcoming, they encourage them. Otherwise, they say, don't get this rubbish in and they throw. So this natural curiosity of looking down on Earth and trying to figure out is what geology is, and astronomy looks. Yeah,
Actually.
yeah.
So another, I think so, one of the last questions. The data in the catalogs are extremely huge. Can laptops or desktops, which have a considerably weak computing power as compared to huge supercomputers, actually handle the huge amount of data?
That's right. Yeah. So, see, one thing is you can, if you want to download everything in your system and work, it's getting more and more difficult. So now, on these websites, you are allowed to create your space, and you program. You do cloud computing. You log on from your system. The data is lying somewhere in the internet, and you are running the programs there rather than locally. So that's the solution to this. And so you are using cloud computing, cloud storages where you can. So even in these sites, a Hubble site, and you can store a certain amount of data right there and work on it right there. And only after having processed and worked, you can download it on your system. Because if you try to download on your system and your systems are slow, things will be a big mess. Other than that, there are certain institutes which have supercomputers, multi-core processors, and so on. And they are, if you are lucky, you can use them. Many a time, people are pretty reasonable. Like in Hyderabad, next to our university, there's Triple IT. They have clusters, big supercomputing systems. And when we approached for our research scholar to do galaxy dynamics and so on, she was running something on a system which would taking her, 1 month to run one simulation. So we took time and went there, and now she is running with many more particles, but in a much more efficient way. Within a week or so, it gets done, and you can work on these systems. So Ayuka has one such system. All big universities have. So if you are serious minded, I'm sure they'll permit them to use it. The other opportunity is to work on the cloud. Yeah, you can use resources on the net and do it there. Yeah.
Right, sir. Thank you so much, sir, for the valuable information and the insight of the open data sources, which we can actually go through and do our research work also. I would request all the participants to kindly switch on their cameras for a group photograph. Yeah.
Only few people are turning on their camera. Please turn on your camera so you can just capture this. Everyone. I'll just request you all to turn on.
A lot more. Don't be shy.
Everyone, please turn on your camera.
Right. Thank you, everybody. Thank you so much for coming.
Thank you. Thanks, Anna. Thank you.
Sir, we would definitely like you to give us some more lectures on Simbad and TopCat even, because I had attended a few sessions with Priya ma'am regarding TopCat and DS9, how to use it. But still, many of us would definitely like to learn more on that.
Right. So we can have a session for each one, and in a systematic we can go, because it takes time for
Yeah.
various sessions. Yeah, so
Yeah.
we can do that. No problem.
Definitely, sir.
Yeah.
Thank you.
Yeah.
Thank you so much, sir. Thank you so much.
Okay. Bye bye.
Thank you.
Bye-bye.
Thank you.
Okay, sir.